so I'm Milano. I'm a professor at Princeton, and I don't work on the beam. But what I do is I work in programming distributed systems. And I'm here today to tell you about it. And let me start by telling you that programming distributed systems is hard. Applications like, say, PowerPoint, that used to run on a single thread of a single computer have now become concurrent, or distributed, or even geo-distributed. And as our applications have increased in scale, our ability to program them has not kept pace. The results are predictable, an endless parade of bugs and vulnerabilities as programmers wrestle with each new leak in what was once reliable abstractions. This is where we are today. We've built a cloud, yes, and we've put our presentation software in it, but we don't yet know how to actually program it effectively. This is where my work comes in. I'm here today to give you a little bit of a, oh no. I'm here today to take you on a short tour of some of the work that I've done in this space, solving the problems of programming at scale by solving everything from destructive data races on single machine computers to handling coordination overhead and consistency errors in large-scale distributed systems. But before I can tell you about any of my cool solutions, I should tell you more about my problems in particular. What is a data race? What sources of coordination overhead am I worried about? And what are examples of consistency errors to avoid? I'm glad you asked. Let's start with the data race. A data race occurs whenever two or more threads simultaneously access a single piece of memory, and at least one of those threads is writing. A classic example of a data race would be a split increment. This occurs when, say, two threads, the gray and orange thread, are both simultaneously trying to increment a value stored at the same place in memory. What can happen here is that in between, when the gray thread reads the value that they intend to increment and go to write it back, the orange thread can read the old value, causing the increment effect of the orange thread to be lost. This in particular would be an example of a destructive data race. Just a data race where the non-determinism of interleaving actually affects the program outcome and causes a bug. Now, you may argue that the programmer clearly intended for the second increment to do nothing, but I would argue that in this example, the programmer did not want their increment lost. And this has been around for a while. I mean, raise your hand if you've seen or heard of destructive data races before. Yeah, great. And we've solved it many, many times. In the context of sort of distributed or concurrent programming, a popular solution class is transactions, especially in databases. And transactions introduce this abstraction of atomicity. They give us the ability to group our code into individual units that appear to execute all at once, allowing either the gray thread or the orange thread to go first, concretely. And it works, but it's actually kind of slow, especially at smaller scales when I'm trying to run it on, say, shared memory. But we're just doing definitions, so put a pin in that, we'll get back to it later. For now, we've defined what our data race is. Now let's talk about what coordination overhead is and how it can lead to consistency errors, or vice versa. So when I'm talking about consistency in this talk, I'm going to be talking about the analog of shared memory consistency that occurs in distributed storage systems, in particular replicated distributed storage systems, where instead of having one database, I have multiple copies of that database on different machines. The strongest consistency model that we're going to talk about today is going to be linearizability. But before I go into that, let me talk about what a consistency model is. It's basically a set of rules that govern what happens if you perform a write at one replica or copy, and then you attempt to perform a read at some other replica or copy. Like I said, the strongest model we'll talk about today is linearizability. Linearizability says that if I perform a write at any replica, then I wait any amount of time and perform a read at any replica, I'm guaranteed that the effects of my write have propagated to all replicas before my read is allowed to execute. It's basically the gold standard. It lets you ignore all of the concurrency and replication and distribution here and treat everything like it's just one machine. But much like transactions, it's actually somewhat hard to implement efficiently, working best at small scales, like geographic scales, like single islands, like, say, Paxos, which is the name of an island in Greece. And this tends to be our sources of coordination overhead. Now, while these things work fine on small scales, they start becoming really difficult to implement on large scales, especially global scales. When your distributed database has been replicated across continents, you have to deal with some unfortunate physical realities. In particular, the speed of light is surprisingly slow. It's only about 4 inches per clock cycle. And these continents are many more than 4 inches apart. At this scale, you've quite literally outgrown small islands like Paxos or well-known distributed consistency protocols like Paxos. And you'll have to accept the fact that your replicas will temporarily diverge. Now, some systems operators have just sort of embraced this and decided to expose this divergence directly to the programmer via weak consistency. Under weak consistency, which is an umbrella term for a whole bunch of guarantees, the common thread is that if I perform a write at some database, then I await any amount of time, and I perform a read at a different replica of the same database. I'm not actually guaranteed that I'll see the effects of that write. While I am guaranteed my writes will eventually propagate to the other replicas, there's no real time constraint on when that might happen. This is a hard abstraction to program against. We're basically exposing the user to time travel, allowing them to read the present today and the past tomorrow. And this fact is so well known that some actual databases have been named after time machines. If you're not familiar with the blue box, this is a small box that used to be on the streets of England where they would store criminals temporarily. It's also a time machine from a TV show. And programming against that is going to be our primary source of consistency errors. Okay, those are our problems. Let's start with solutions. We're going to start at the largest scale first, handling consistency errors in globally replicated databases. And let me begin by saying that there's actually some applications that can handle this just fine. Consider, for example, an online game service that wants to record wins and losses of their players, perform matchmaking so that players of similar skill fight each other, and run tournaments where they invite the 10 best players in the world to contest for blood and glory. I would argue that some aspects of this are fine with this weak consistency behavior. For example, records and wins and losses. If I'm playing Smash Online and I just destroy you in 5 seconds, I'm actually kind of okay that the world doesn't know that instantly. I'm okay if it takes minutes or hours or even a day or two for my glory to reach the furthest ears. Meanwhile, things like running tournaments, I might care a bit more about being correct. If I say that I want to invite the 10 best players in the country to my tournament, I should invite the 10 best players in the country to my tournament. It is exactly this domain for which we built the language mixed-D, which is a new programming language for writing distributed transactions with mixed consistency requirements. The goal here is to keep everything as weakly consistent and therefore as fast as possible without affecting application correctness. Let's see how mixed-D looks. Oh, wait, it's got a paper. All right, let's see how mixed-D works in the context of our example. So we were going to record wins and losses and have a ranking of the best players, which means we were going to want some tables. A table to store our wins, to store our losses, and to store the rank of our players. We're also going to want some transactions that manipulate the data in these tables. For example, this match transaction takes 2 players, records that one of them has won and one of them has lost. Now I'm going to pause here for a second and say that all of the code you'll see in this presentation is real. It's code that is very accurate to what you would write down in my languages. There's no missing preamble, there's no accidental keywords I'm leaving out for simplicity. This is just what you write. And I personally think that it's accessible and simple to an audience that's like seen Java before. Not that I'm saying any value judgment on Java as a language. And because of that, I'm going to actually give us enough time to read the code while I vamp and say things like, I'm giving us enough time to read the code. Okay, back to the talk. Now, we also might have a transaction like this invite to tournament transaction that is meant to maintain the list of ranking. So in this transaction, what we have is we've got a list of the best players in the world, or rather we've got an empty list that will contain the best players in the world. Then we iterate through the first 10 players in the rank table, so players 1 through 10, the best 10 players in the world, add them to our list, and then return our list. What this transaction does, gets us the 10 best players in the world, so that we can send them an invitation to our tournament. Now, one particularly interesting part of this might be that there's words on these transactions. The programmers helpfully annotated them with weak and strong to express the programmer's understandings of what the consistency requirements will be for their application, much as I just motivated a couple of minutes ago. Mixed will see these annotations and will automatically determine that that means the wins and losses can be stored on weakly consistent storage, whereas the rank needs to be stored on strongly consistent storage. So far, so good, but also pretty much standard for databases. If you've ever set an isolation level during a transaction statement, this is a very similar effect. Where Mixed really shines is in its ability to recognize that consistency composes across transactions. And let's illustrate this with a third example, a transaction for actually calculating the rank that'll go into the rank table. This transaction is much larger physically, but it is not much longer. I'm just going to take longer to go through it. So we'll start with an empty list containing the win-loss ratio of all of our players. Then we'll iterate through all of the players in the world, dividing their wins by their losses and adding them to that list. We'll then sort the list by the win-loss ratios, so the list is now in rank order, and we'll use the list to assign the rank table in that order. Remember how I said this is going to be real code? The gross bit in the middle there is just projecting out the player component of the win-loss ratio player pair, so that we can actually have a list of players, not the list of ratios. Okay, now I didn't warn you, but this is a somewhat interactive presentation. So, who can spot the bug?
Losses zero.
Yes, everyone loses in my world. That's correct. We have a divide by zero error in wins versus losses. That's actually not the bug that I was hoping we would see. However, it is a real bug, and there is a reason I did not fix it. It's because fixing it doesn't fit nicely on that line. So we've left it in the talk. But assuming for a moment that I just make everyone lose at least once, can we find a second bug? Yeah.
The wins and losses aren't guaranteed, right? When you pull the data out, because it's weak.
Rephrasing that, there's no real guarantee that I'm looking at the right replica for my wins and losses, or that there even is a right replica, because it's weak. And let's illustrate what I mean by that. Remember, these are all replicated databases. In particular, the wins and losses are going to be recorded at multiple different replicas of our causally consistent database. But the transaction we're running to calculate our rank will only be run at a single replica of our database. While the invite to tournament transaction will run with strong consistency against a strongly consistent database that can pretend like it's a single machine, by the time we run that, it's too late. We're not going to get the 10 best players in the world. Instead, what we will get is a bunch of angry emails from people looking at different replicas who think that they're the 10 best players in the world. This is a terrible outcome. What we're seeing here is a violation of an important principle, a bug that we caught in the audience, that we'd like to enforce for the composed distributed application. In particular, that strong outputs must stay strong. Or more formally, that strong observations, like the list of the top 10 players for our transaction, shouldn't be influenced by weak data or weak operations, like the replication delay between the wins and loss tables. Now, Mixed is able as a language and compiler to automatically recognize this at compile time, and to tell you that the calculate rank transaction is fundamentally flawed. And we'll go into how that happens in detail, but I do want to confess something first. So far in this talk, I've been saying that there's weak and that there's strong. And I've been kind of identifying strong with linearizability and weak with this sort of eventually consistent notion. But in practice, there's a lot more than weak and strong. there's a whole lattice of different consistency models that give you different combinations of strong guarantees and weak guarantees. And conveniently, for all of the models that are in common use in this lattice, there's one strongest one that is stronger than all the others, which is linearizability. And there's one basic guarantee that everyone will always give you, which is eventual consistency. This allows us to sort our various consistency models in an order, where the higher up you go in the order, the weaker your guarantees get. And the further down you go in the order, the stronger they get. And I didn't make this order up. This is from 2016, from someone else's paper. Now, using this ordering allows us to give us a formal definition of what improper influence is. Improper influence is guaranteed when a less consistent read, so something up in this order, influences a more consistent write, so something down in this order. It's also guaranteed when two things that are incomparable in the order influence each other in any direction. And Mixte's observation is that we can prevent this kind of improper influence by using an information flow type system, which is from the security literature, in which it is frequently used to protect data's integrity or confidentiality. What an information flow type system does is it allows us to syntactically track the influence of individual operations through the course of an overall program in a composable way. And I'll illustrate this by showing us how Mixte is able to recognize the calculate rank transaction is wrong. So we're going to start with some base knowledge. Mixte originally assigned the rank, wins, and losses to various tables of different consistency levels based on annotations provided by the programmer. So we can use that as ground truth. Mixte then, statically at compile time, is able to see that the wins and losses will influence the win-loss ratios list, and can in turn see that the win-loss ratios list will influence the rank. Upon seeing this, it can derive a contradiction. The rank was ground truth, supposed to be strong, but it's now influenced by something weak. And it can signal an error to the programmer. So at this point, the compiler tells you you're wrong and you should go home. But you might still want to run tournaments, so what are we to do? Well, we don't just stop there. We also give you a little bit of guidance as to how to fix it. And this is really where we start getting different from information flow in a security context. See, individual databases, even if they're weakly consistent, will frequently allow operations that temporarily increase the consistency of the overall system. For example, if I'm a weakly consistent replicated database, I could just pause the world for a second, wait for all of my transactions to finish and synchronize, and then for a brief moment in time, I can actually read a consistent result across the entire system. And Mixte will allow you to expose those primitives directly in your transactional code. This quorum read, for example, in our hypothetical database, allows you to read from the entire set at once, performing all of the reconciliation directly. It counts as a dynamic upgrade for the consistency. Mixte is able to recognize that the runtime effect of this read is equivalent to having read from a stronger store. And it will consequently label that as strong. At this point, everything in the system will flow to strong, and the transaction is blessed. If you're thinking in the security literature about declassification, I should note that this is not precisely equivalent, and we can talk about it later. Okay, I should also note that this system was for preventing flows in a bad direction from weak to strong. You can always flow in a good direction from strong to weak. For example, if I run this invite to tournament transaction and then I turn around and send email to the first 10 people in the list, that's never going to be an error, even though email is perhaps the most weakly consistent thing I can think of. This is what Mixte manages. By using information flow types to prevent improper influence, we are able to enforce that important semantic property, that strong outputs must stay strong. And that grants us reasonable semantics for our mixed consistency transactions. A good language design, but not just a language design. Because like everything I'm going to tell you about today, Mixte is implemented. It's a real system. In particular, it's built as a deeply embedded DSL in C++ that serves as a shim layer atop traditional databases and data stores. You can download it, you can use it today, but I should warn you, it is a 15,000-line implementation that is deeply embedded in C++. It will not run on the beam. Now, Mixed answers a lot of questions about how to use distributed consistency correctly. But one thing it still relies on is annotations by the user. And all it can enforce is that the user's annotations are respected. It has nothing to say about whether the user was correct in saying that they wanted this to be strong or they wanted that to be weak. So it still has a bit of a question. How is the user to know when those annotations were warranted? How is the user to tell if they've gotten it right? To put that differently, is there a way that we can help? Is there a way that we can identify a class of programs that will always be correct under weakly consistent observations or weakly consistent operations? And this is going to be the next batch of papers I talk about, which will use this to handle coordination overhead. What we're going to need is basically a set of reliable observations which will allow us to work with weak consistency. Now, a reliable observation isn't like a term of art. It's not a known thing in the field. I made it up for the talk. And for the purpose of the talk, a reliable observation is any observation which is able to form a guarantee about distributed state. For example, if I'm in a traditional database and I start a serializable or strictly serializable transaction, and I perform a read in that transaction, that read is a reliable observation. For the duration of my transaction, that is a guarantee about the value of the read distributed state. But there are other examples too. For example, if I were to go back to my game tournament and check to see if the wins of a particular player was at least 15, and I see that their wins are indeed at least 15, this is a reliable observation, because your wins in the system will never go down. You saw all of the code for this tournament, and never can I decrement your wins. No concurrent mutations can violate it. So even though we may be missing some values for your wins, even though your wins look to me like they're 16, but in practice they're 4,392, they're still over 15, and they're not going to get any less over 15. This winds up pointing to a general observation, that the more you restrict the allowed mutations on your state, the more general the observations you can make while keeping those observations reliable. There's kind of a spectrum. On the one extreme, we have things like constants, where under arbitrarily weak consistency, every single observation is reliable, because they're constant, they don't change. I cannot affect the value 7. Ever since Python 3.1, I cannot affect true or false. On the other extreme, we have things like single-writer or multi-writer registers, values I can arbitrarily reset. And the moment I've written to that, I have no idea what it is anymore, because someone could have come in a millisecond after me. But we've got some useful stuff in the middle. Things like counters are wins and losses that are only ever incremented, or sets that are only ever added to. This is a class of data types that grow monotonically. They get bigger. They inflate according to some particular order. And they allow us to perform a certain type of observation, a threshold observation, where we can compare them with stable predicates. Those will always be reliable. In other words, if all of our shared objects only ever grow, and if we only ever observe thresholds or stable characteristics of our objects, then our programs can be correct and even convergent, like deterministic, under weak consistency. And we relied on 0 transactions and 0 runtime mechanisms to enforce this, which means as an added bonus, we've avoided all the coordination that normally comes with replicated storage systems. Amazing, right? Okay, how much can I actually get away with just incrementing things and building out a distributed system? A lot, it turns out. So surprisingly, many core system components are fundamentally monotonic. And rather than just assert this, we showed this by building out a distributed system powered by monotonicity at its core. This is a programming languages audience, not a systems audience, so I'll just quickly say that this is a replicated state machine system, which means that it allows you to use the abstraction of a single computer backed by multiple copies of that computer where all the copies are kept completely in sync, much like the linearizability example from before. The system is performant and effective. It was benchmarked at around 10 times faster than its state-of-the-art competitors when we released it. We've presented it at major systems academic conferences, and there are systems that have been built on top of it. And at its core are monotonic protocols over monotonic data structures in a monotonic language. It's also a paper. Rather than go over the language exactly, I'm going to show us an example of a particular core protocol that's necessary for any distributed replicated state machine system to work. And this is basically just a voting protocol for message delivery. So let's say I've got 3 replicas in my system, replicas A, B, and C, and I want a message to arrive at these replicas consistently so that it either is seen at all of them or seen at none of them. Normally, the way this protocol works is the message will start at one of the machines, say A. That machine will forward the message to the others. Those other machines will react by acknowledging that they've gotten that message, sending that acknowledgement back to A and the entire rest of the system. And when the system has seen all of the acknowledgements from all of the participants at every location, we can conclude the message has been delivered. So if B sees all of the votes from A, B, and C, then B knows the message is everywhere. We're going to implement this in terms of a single monotonic data structure, a simple shared state table. In this table, cells, individual values, are restricted to containing monotonic objects like counters or sets. That'll support monotonic update, functions, and threshold reads. Intuitively, columns are going to correspond to individual data items, and rows will correspond to individual replicas. So the top left here says the value of X at A. Okay. We've also built a custom DSL on top of this table to enforce this monotonicity property, that you can only actually inflate the values in the cells, and you can only read them by doing threshold comparisons or other monotonic functions on them. Let's use this table now to re-implement our stable message delivery. So we're going to start with the message on machine A. And of course, what will immediately happen is that machine A will believe that it has received a message from itself. Excellent. Now we'll send that message to machines B and C. All right, what happens now? Well, machines B and C will mark in the table that they've received a message from A as well. While all this is going on in the background, there's a thread running that's checking to see if the minimum of this column is at least 1. Minimum is a monotonic operation. Comparing with a constant is a threshold operation. This is monotonic, this is allowed. And when this column gets to at least 1, we know that we've received a message from A everywhere. And we can conclude that our message is delivered successfully. Very cool. Now, I promised, of course, that we were going to avoid coordination overhead by doing this, and it sure looks like I have a giant centralized table here. So let's change our story a little bit. Rather than having a giant centralized table, we're going to actually have a replicated table, where every machine has their own copy of the entire table, their own view of what the overall state of the system is. And let's rewind our example for this replicated state. Just like before, a message arrives at A and we receive from A. Now we send the message, and just like before, B and C will mark that they received a message from A. But now they're doing that in their replica of this table. So there is no individual table at which this column is 1 yet. We've still got that thread running in the background, but it's not doing anything because we've not yet reached 1. We're under weak consistency here, so in the background, all of these table states are slowly replicating, and eventually we get to the point where there is a 1 everywhere, at which point this deduction can fire. Same exact protocol, same exact results, different latency considerations. Using just tables like this, we were able to build strongly consistent consensus, or 95% of it, atop weakly consistent replication. And by leveraging theoretical results about monotonicity under weak consistency, we can get properties like convergence and race freedom entirely for free. Basically, monotonic programs just can't have destructive data races. It's mathematically impossible. So we've saved the programmer from needing to reason about things like message interleavings or reorderings or replica delay for correctness purposes. This is a classic example of how careful language design can build better distributed systems. And just like before, this ratio is a real system. Still written in C++ though, but this one's a bit more robust. You can check out the project on the link. Good example, but turns out that not everything is monotonic. I said only 95% of consensus. You remember this graphic from like a half hour ago? I told us that we were going to put a pin in this and come back to it later. All right, let's take that pin out now, and let's return to the world of shared memory programming to talk about how to handle destructive data races in cases where we really don't get to rely on monotonicity. This is going to be our last area of the day. I've written a new type system, a flexible type system, for allowing fearless concurrency. What this means in particular is in a shared memory system, you will have updates, you will have concurrent mutations, you have multiple threads, and you will never have a destructive data race without excessive annotations or excessive runtime overheads. Also a paper. What our type system is going to have to enforce, I should have said, this is done by a type system. Most of these things are done by type systems. I don't think I was clear on saying that. This is a type systems talk. Okay. What we're going to enforce here is mutual exclusion. We're basically imagining a world where we've divided up our memory into sets that are dedicated to individual processors or individual threads, and large portions of it that are governed by locks. If a thread wants to write to memory outside of its little private zone, it needs to acquire a lock in order to do so. Okay. Have we seen this before? Hands up. Awesome. Like 4 people have used locks before. This has been the common solution, especially in sort of imperative shared memory space, for decades. I think it's been about as old as operating systems research itself. The original paper that introduces the idea of a lock is by Dijkstra, and it does so in a footnote, because it's way more interested in talking about process overheads. And I think it's from like the early 70s. Yeah, so it's been around for a while. And the hard part of dealing with shared memory programming with locks is not the whole having locks. It's not the designating that the lock shall guard a region. It's not the acquiring of the lock. It's the releasing of the lock. See, if we look inside the memory here, while our gray thread holds our gray lock, it may choose to form references between the objects that it owns and the objects that the lock guards. And that's fine. That's the point of the lock. As long as they hold the lock, they should be able to do whatever they want to the memory it guards. But once they release the lock, they should no longer be able to access, or at least they should no longer use their ability to access any objects the lock guarded. That means that the programmer of the gray thread needs to know where these references go. They need to know the difference between a reference to a locked object and a reference to their own. And it turns out that the challenge of tracking references in an arbitrary imperative programming language with shared memory is undecidable. You literally cannot write an algorithm to do this in C. But that's okay, we're programming languages researchers. We solve undecidable problems for breakfast. And this particular undecidable problem has been solved a few different times, perhaps most popularly by Rust. And Rust allows a particularly elegant solution. Just make everything trees. In particular, Rust allows at most a single inbound reference to point to any data object anywhere. And the challenge of tracking one reference into a locked region is way more tractable than the challenge of tracking arbitrarily many references. There is still a problem, though. It turns out, work with me, that not all data structures are trees. Consider, for example, a doubly linked list. Let's say that I wanted to write a doubly linked list in Rust. So I would write the obvious thing and it wouldn't compile, and then I'd say, that's okay, the internet's done this before. And maybe I'd open up GitHub Copilot and I would write a doubly linked list and it would do the obvious thing and that wouldn't compile either. So then I'd finally start Googling around. And I would learn a lot about this thing called stacked borrows. And I would be reassured many times that unsafe is fine and you can just use it. But if I wanted to stay in safe Rust, I would ultimately be left with something like this. This is awful. I mean, the font's a little small. I didn't syntax highlight it at all. But beyond that, it's got all these little layers of types. And every single layer of type here is going to add a little bit of runtime overhead to track a property that we already know holds. And it's also cheating. My goal was not to use unsafe, even though the internet said that was okay for this. But what these libraries are going to do is use unsafe internally. And full credit to these library authors. A lot of them have gone and used interactive theorem provers to go spend hours or hundreds of hours of grad student time to prove that their use of unsafe is fine, actually. But I don't want to do that. So I built a new language. And I can do better. One keyword, no runtime overhead, no weird type wrapping, pretty natural code. So how was I able to do this? And Rust decided not to. It turns out that when you do this, you run into a problem. And I like to call this problem path confusion, which occurs whenever two syntactically distinct paths might or might not point to the same object at runtime. All right, let's take a closer look at this doubly linked list. So here I've illustrated our doubly linked list with little blue circles to represent the spine of the list, next and previous pointers in blue to represent the next and previous, you get this. And the important part here is I've got this red pointer payload that connects the individual list node with the payload stored at that position in the list. And this individual payload has the one keyword on it, this ISO keyword. ISO here stands for isolated. It means that there's only one reference that can point into the abstraction on that line. In other words, there's no other red arrows secretly not illustrated that can point into the green box. There's only one way to get there, and it's through the red arrow from the individual list node position. This isn't enough. This is the sort of thing that Rust's uniqueness gets you all the time. This is the sort of thing that a unique pointer in C++ gets you, and this isn't enough. Let's see why. Consider a code fragment, where what I'm going to do is I'm going to take the first and second elements of my list and send them to two distinct threads. So first I'll take the first element, the head of the list rather, and assign it into this head temporary. I'll take the second element of the list and assign it into the second temporary. Then I will send the heads payload to thread 1, the second payload to thread 2, and then the sending thread will exit so that we definitely can't race with thread 1 or thread 2. Now a type system's job is to look at this and decide, is this code safe? So, type system, is this code safe? I should also note that, like everything else in the presentation, this is like real code. There are some things going on here that might seem impossible or illegal, like temporarily aliasing things onto the stack. That's totally fine. That is not the danger. And my type system is going to allow that just fine. So no one's willing to commit, but we have one over there.
If head and second, the next point to the same point to itself, you can't send the red arrow to two different.
Yes. I have promised that there's exactly one pointer to that payload, but I haven't said anything about whether head and second are the same object or not. In this example, I've got a circular linked list of size 1. And this circular linked list of size 1 is a totally valid instance of this data type. It's got a next pointer to a list node. It's got a previous pointer to a list node. I never said a different list node. It's got an isolated pointer to that payload, and there's no other red arrows coming into that payload at all. But now when I run this program, head and second are the same, which means head.payload and second.payload are the same. And I've got a data race. The bug that I made, the bug that it took us a few minutes to decode, is that we've wrongly assumed that head and second will always be different. We've effectively wrongly assumed that this is a valid doubly linked list of size 2, or at least 2. This is path confusion. How are we going to solve this? Well, what we're going to do is we're going to build an abstraction of the overall heap state in our type system. See, while the syntax and while the traditional class of our code is going to give us something that looks kind of like this, we're going to simultaneously, at type time and at compile time, model it like this, where we're going to only preserve the pointers that are ISO marked and just merge everything else that's connected by pointers into one big blob, which we like to call a region. This ISO keyword will enforce and establish the statically enforced boundaries between regions. What this means is that statically, we think that head and second might be the same because statically we see this big orange blob that covers both of them. But what it also means is that we can't do concurrency between head and second. That because we think there's everything in the orange blob might be the same, these regions, these things connected by pointers that are not isolated, all wind up forming a unit for concurrency purposes. If I send anything in the blob, I will send everything in the blob to a new thread. Now, if that seems pretty restrictive, then that's okay. We'll put an asterisk on it. Should have put a pin in it, because we can fix that. But yeah, basically the way this works is the code looks both at, or the type system rather looks both at this abstract region view, and it looks at the individual object view. And it'll only allow code that is safe according to both views. Safe when we look like we've got one big object that everything points to in a single region, and safe when it looks like we have individual objects that everything points to in a region. And yeah, that's basically the solution. And we can, of course, recover some of the concurrency that it looks like this solution loses. For example, if we actually knew for some reason that our list had 2 elements, then we could reflect that knowledge dynamically into the program, and the program would take advantage of that. This if distinct keyword is built into the language, and it's true whenever head and second are different. In that case, we know that there are therefore 2 payloads, because if head and second are different, and if their ISO pointers are always unique, there must be therefore 2 different ISO pointers to 2 different payloads, and that will allow us to send to the 2 different threads correctly. We also allow an even more intensive solution, where what we will do is we will actually split the entire region. If head and second are fully disconnected, if say I've split my list in half, and I've sent half to one thread and half to another, grand. Now I can split the orange blob entirely, and I can treat them as different things for concurrency. Now this is just a taste of what the type system can do, but using these features, we've managed to build out a fully featured library for collections, including many operations that would not have been possible in Rust, and many other operations that would not have been possible in any rival systems or languages. It works. We have been able to provably eliminate destructive data races at compile time, compiling thousands of lines of previously impossible examples without any automatic dynamic overhead. And we've made this into a proposal for the Swift language, which they have assured us has been favorably reviewed now. So you can check it out on the Swift forum to see their comments. And I think that's where I want to leave you. Over the last 45 minutes, we've seen ways to solve problems of programming concurrently and at scale. We've seen how to solve destructive data races, handle coordination overhead, and even handle errors that arise from consistency. Thanks, everyone.